Hey guys, and welcome back to class. Today's video, we are specifically going to be speaking about what's known as Ohm's Law. So specifically, this video is dealing with Ohm's Law, and we're looking at the relationship between voltage and current and resistance is what we're going to be targeting in this. So I use this word resistance, and we've talked about it just a little in one of the other videos. One of the other videos we looked at, we were actually looking at like this tungsten filament light bulb. And we said some things we consider, say for example, copper and gold. We consider those to be good conductors of electricity. It means they let electrons freely flow through them. On the other hand, this tungsten, or if you're being good and periodic with it, it's actually in Latin. I think it's called like wolfram, but don't ask me how to say that correctly. I'm from Alabama. That's my excuse for everything when it comes to enunciations. But this whole thing about the tungsten filament light bulb, and here's that close-up view. Tungsten is a very, very poor conductor. Matter of fact, it's such a poor conductor, we consider it to literally be a source of resistance. And what happens is, as those electrons try and fight through this filament, you get basically electrical friction. And what it does is it gives off a lot of heat. And what happens, it gives off so much heat that the light bulb glows. Now, in electronics, one of our most basic components is what's known as a resistor, because a lot of the time what we're actually trying to do is we need to literally limit the amount of current in a system. I was, no joke, just the other day I had some little neon bulbs that I was playing with. I had some neon bulbs, and you will blow those bulbs easy if you hit them with much voltage. So I was literally taking a resistor, a little component that looked like this. We used this little squiggly line symbol to represent it, but I was using a 100 kilo ohm resistor in series. I was soldering them together so that I could let kids basically send static electricity and make the lights blink. But what happens is, if you don't have something to limit the flow of current, letter I, passing through the system, well, what happens is you blow the little bulbs. Granted, they don't cost much. They're like maybe 60 cents a bulb, but still, I don't want to be blowing those things. So we use like a material like this one's made out of carbon or in the inside. It's a ceramic carbon mixture, and by doing that, it controls or limits how much current. Again, if you can imagine, it limits how many electrons are able to pass through this. And if you're wondering, like, Mr. Cole, what are these colors for? Well, just so oddly enough, the colors actually tell us what the resistors are. So literally, you'll notice there, and I'm going to write this, 1, 2, there's 3 bands. This 4th band is always either a silver or gold. Hey, isn't there a Christmas movie that has like silver and gold? Never mind, I won't do that here. But this silver or gold is what's known as a tolerance. So the silver band tells you that like whatever the first 3 bands say this resistor is, the silver band says we guarantee this to be within 10%. The gold band, on the other hand, and these don't have gold, but sometimes you'll see gold, and what gold represents is 5%. So it guarantees within 5% to have that value. Well, check it out. So what about this wonky looking thing? Well, this is a ceramic core, and you got a piece of like nichrome wire wrapped around it, and it's got a pretty high resistance, not so much that it glows, or well, you're hoping it doesn't glow. You don't want your electronics devices to catch on fire. But this is still, it's the same concept. This is a very large type of resistor. Some of these are actually wire wound like this, and they'll have like an insulative coating on the outside so you don't actually see the wire. But they're all different types of resistors, and resistors are used in all forms of electronics. Go right now, find something around your house, electronic, break it open, and look inside of it. On second thought, your parents could really get mad at me right now if you did this. But we use resistors for things as simple as making a light that blinks. Involves about 4 resistors, a couple of transistors, a couple of capacitors. We use them for what's known as filters. We use them to literally, like in my circuit the other day, limit the amount of current that's in there. We use them, probably the easiest example I can give you is this. Let's say you've got a circuit, and let's say the only form of voltage that you have is like a 6-volt battery. Well, what you can do is this. There's a device known as a voltage divider. And what happens is literally by the use of 2 resistors, we can actually get a output voltage in the middle. So by the use of 2 resistors, we could say change that voltage to 3 volts. So at this point, you should have multiple things for me. Mr. Cole, what do these colors represent? What do these squiggly lines represent? By the way, those are some of the worst squiggly resistor lines. Well, obviously, when you're drawing electrical diagrams, we don't actually draw resistors. We use symbology. We don't actually draw batteries. Like here, this represents a DC power source or a battery. So we actually have symbols that we use to represent it when we're drawing a circuit. So this is, and if you needed it, I'm not going through it. This is like a little generic list of the types of symbols that you see. There are obviously more than this. I didn't even put like symbol for a, I didn't even put the symbol for a transistor in here. So there's obviously more, but for the sake of what we're looking at, especially for general physics and physical science, we're looking for resistors. A variable resistor, if you have a volume knob, a literal knob on a radio, that's actually essentially a variable resistor. As you turn the volume, I think in the words of Leonard Skinner, turn it up. As you turn up the volume, you're actually turning down the resistance, allowing more current, which is actually what makes the speakers get louder. So you're kind of getting an idea. Here's a symbol for an ammeter, for a voltmeter. Galvanometer, you've heard me talk about that before, and I'll talk about the end. Capacitors, we haven't discussed yet. AC electricity, alternating current, we have discussed, and this is what a ground is. So we're going to look specifically at some resistors. Now, I'm going to take this is going to be a 30-second crash course in reading resistors. So all you need is like this color code that you see in front of us. So here's the color code that we have, and this tells us everything that we need to know about a resistor. So say, for example, remember I told you like gold and silver, that's always the last band. That's like your tolerance band, your fourth. So look up at this resistor, yellow, violet, and red. And what it tells me is this. If you look at the chart, it says that yellow is represented by the number 4. And it says that, what's next? Violet is represented by purple is represented by the letter 7. My hardest time in real life is on real resistors, actually figuring out the colors. Now, the cool thing is this. The last band, band number 3, notice how I put a little X there. It's a multiplier band. So if it says multiply by 0, you don't actually multiply by 0. It just means there's no multiplier. So like if this had a black band on it, it means there is no last band, there's no multiplier. Your answer would just be 47 ohms. That's it. If you had a brown band, you would literally multiply by 10, 1, 0. So if this was a brown banded third resistor, we'd multiply by 10. This would be 470. Well, this is a red resistor, or red third band, which means we multiply by 100. You should be able to figure this out. Multiply by 1,000. You just keep adding a 0. So brown means multiply by 10. Red means by 100. So all you have to do is this. 47 times 100 means this is a 4700 ohm resistor. Take a look over here. Brown, black, and red again. So we know that brown is a what? Brown, according to our chart, is a 1. Black is 0. And red means you times by 100. So this one is a 1,000. Except for me, I wrote 100. 1,000 ohm resistor. So it's not really hard. Try this one on your own. Red, red, orange. So I'll pause for a second, and what you got? Red, red means 2, 2, and then orange means you would multiply by what? 1,000, 3 zeros. So your answer is 22,000. So it's got you a basic idea. So here's the deal. In the lab that we're doing today, we want to explore this Ohm's law. So if we were in the lab right now, what I would actually have you do is build a circuit. I would have you build a circuit using a power supply, a DC source, and I would have you then hook an ammeter up in series with this circuit, connect it to a resistor. Hopefully you would draw a better one than mine. I would connect my circuit, so we need a complete circuit. Now, something is very important. Notice how this ammeter is being backed up by this resistor. This ammeter always has to be, we use the word, whenever you're using an ammeter, and I'm putting so much detail in this video because I hope you're back in a lab one day, and when you are, I don't want you blowing up my equipment. This ammeter always has to be in series with a form of resistance, because we're literally using this resistor to protect the meter. An ammeter has no resistance, basically, on the inside. So that means all this current would flow through it, and you would essentially cook your ammeter. Now, the voltmeter is a little bit different. The voltmeter, I'm going to put a little V here. This is the circuit we're going to build. A voltmeter, they're almost bulletproof. They have a huge resistor on the inside. So a voltmeter, why am I writing the letter P? A voltmeter, now I know why. It's because we always connect voltmeters parallel in the circuit. And I'm going to play with a little circuit, and then I'm going to pause this. So let's build this like we were in a lab. Well, we're not in a lab, so we're going to have to do it virtually. So I want a resistor and an ammeter. Where's an ammeter at? Let's see if I can turn this on. Oh, I got a voltmeter, and here's an ammeter. Now, in real life, your ammeter and your voltmeter would look the same because we use multimeters. I've talked about that in other videos. So in real life, a multimeter like this can measure all kinds of things. But in this video, they've dedicated it to just volts. So, I got an idea. Before I actually use a resistor, let's try something. Let's grab hold of a battery over here. And let's actually build a little circuit like the one I drew, except let's leave out the resistor. So let's get a wire, and I'm going to try and draw it. I like these little things to be straight. This is another FET from the University of Colorado. I would encourage you to actually go to just Google FET University of Colorado, and you can download these FETs yourself. This one, the title is up in the corner of my video screen. Circuit construction kit. And oh my goodness, I just blew up my battery and my meter has 6,000 amps going through it. I have cooked my meter. So I'm going to pause this sim. That's what I said a little while ago. We always have to have, can I break that? Thank you. We always have to have a source of resistance in our circuit. So I cannot just hook an ammeter up without a resistance. So now let's bring this together. I think, are we up? Yep, we're all hooked up. So see, now my ammeter is being backed up by this resistor. So this resistor is actually able to protect my circuit. So let's mash play, and bam. Now we've got a nice steady flow of electrons. Now, one of the biggest things that's going to drive you crazy, if you look, the electrons in this video are flowing from negative to positive. Cool, that should make perfect sense to you. Electrons are negative, so they want to travel towards the positive end of the battery. Yet something I'm going to go ahead and tell you is going to drive you crazy, because it did me when I was like a first college kid. I'm always going to draw the current leaving the positive side of the battery. But Mr. Cole, we just saw in the video the electrons are actually going this way. Yes, I know, but when the first people started out solving problems with current, they always drew current as a positive flow. So then instead of changing the name, we call that a conventional flow. Conventional current? That's right. Conventional current is basically saying, oh, the charge flows this way. Mr. Cole, we just saw it actually does not. Hey, it's too late to start over. Thomas Edison would be ashamed. So we're going to draw our currents backwards, which is conventional current, and we're just going to go on living a lie because that's what we do in science. Wow, I all of a sudden feel very guilty about this, but not so guilty to gripe any further. In the next video, we'll pick back up with here, and we'll actually collect data and get a graph for Ohm's Law. So later, toodles and